Hello everybody and welcome to the NPTEL online certification course on microelectronics devices to circuits. We continue with the lecture which we had done in the previous turn, and that is operation in active mode. We will look at circuit symbols and certain conventions. In our previous discussion or interactions, we had seen that we were able to understand the basic fundamental principles of a functioning of a BJT. We have also seen how a BJT works in a forward active mode. What we will be looking today is basically the common emitter configuration of a BJT, and also known as emitter grounded configuration or common emitter configuration, right. And what we do in this case is that and that is what you can see on this diagram here. I will make it a much better diagram from the point of view of understanding, which is this one, right. So, I have an NPN transistor, I have a BJT, and I have my base emitter junction forward biased, right, and my collector base junction to be as a reverse biased, this one, right. So, let me just draw for you from the circuit point of view, right, and let us see how common emitter configuration works in a sense in this case. So, I have a RC here, right, I have a base resistance RB here, and since this is NPN, so I can just do like this, right, and you can vary this one to a larger extent, and maybe I can reverse, maybe I can fix a value of voltage plus VCC here, right, and I try to take the value of V out from this particular place, right, and this is RB and this is my V in, and it is varying, and I want to take out the output from this end, and this is the collector current which is flowing here, IC. Now, if you be so this is my VBE, base to emitter equals to input voltage, and this is also referred to as VCE, collector to emitter voltage, right. So, I have got VCE here, right, I have got VBE here, right, and I have got plus VCC which is ruling here. If we go back to the previous slide, therefore, you see that if you plot IC versus VCE, right. So, let me plot IC, which is the collector current, versus VCE, which is this potential here, right. This potential here is nothing but the value of V out. If you look very carefully, it is nothing but the V out which you see from here. So, V out, if you find out, will be equals to VCC minus ICRC, right. So, if you can find out how IC varies with VCE, I can predict how my V out will vary with VCC, right. Now, this straightforward linear relationship is there which is available with us. Now, if you look very carefully here, when VCE was equals to 0, right, when VCE was equals to 0, I had 0 current, which is expected also, the collector current was 0, and if VCE is equals to 0, collector to emitter voltage is 0, then I would expect to see a 0 current available to me. Quite interestingly, let me also show to you if I want to plot IB versus VBE versus IB, this is also known as the input characteristics. So, base current IB versus VBE, right, for a fixed value of VCE, right. So, my VCE is fixed VCE, I vary VBE and try to take the value of IB, right. So, if you look very carefully for a fixed value of VCE, this starts to behave like a PN junction diode. So, in a forward bias condition. So, forward bias condition, you very well know that it will look something like this for a fixed value of VC. So, VC is equals to say 1 volt or 5 volt or whatever is there, and if you revert it backwards, it will be approximately equals to 0.7 volts which you see, right, and this will be your base current which will be flowing, because that is how the current in a PN junction diode forward bias characteristics looks like, right. If you go on varying the value of VCE, make the VCE larger, I would expect to see a larger current to flow in this case, right. VCE larger means larger current will start to flow with the same value of, so it will not be like this, it is something like this, right, it will be something like this which you will be seeing, fine. So, this results in an understanding of the input characteristics. Now, if you want to find out the forward resistance of the PN junction diode, then resistance will be del VBE upon del IB will be defined as input resistance of the R input of the NPN transistor. So, it means that my VC is fixed. So, if you look very carefully, my NPN, this I am forward biasing it, right, and I am this I have I am reverse biasing it, right, and I am fixing this one, but now I am varying this one, and I will get a profile something like this. I will get a profile. As a result, what will happen is that this profile will lead to a fact that this implies that if I want to find out the resistance offered del VBE by del IB, and it will be order of few ohms because it is the on state resistance of the diode, and it will be order of few ohms which is there. This current will be the order of few milliamperes to microamperes. 2 microamperes range of current will be there, very small current will be there, microampere range current will be there, and that is what you get from this. So, this is known as the input characteristics of the bipolar transistor, right, input characteristics of the transistor. Now, if you want to plot therefore IC versus VCE, also known as the output characteristics, which is already plotted here in this region, and I can explain to you what it happens. So, for a fixed value of IB, right, your IB is fixed. Why? How IB is fixed? Because your VBE is fixed. So, what we have done now is that rather than changing VCE, we are or VCB, we are changing we are fixing VBE, and therefore my IB is fixed. When my IB is fixed, I vary VCE and try to get the value of IC, right. So, I try to get the value of try to get the variation of collector current with respect to collector to base voltage or voltage which is available with me. Now, when my therefore VCE equals to 0, right, my current will also be equals to 0, my collector current will also be equals to 0, and the reason is that when my VC is equals to 0, there is no electric field on the collector side to accept the electrons which are coming from the emitter side. So, even if there is a base current or even there is a emitter current available, all the emitter current is either going to the base side, because you do not have any potential on the collector side to accept the charge carriers, and therefore the current is 0, and that is the reason the current is 0 for VC equals to 0. As you start to increase your VCE, the current starts to rise, and therefore you see a linear increase in the value of current, right. There is a linear increase in the current. As you make your VCE larger and larger, there is a linear region, and then you enter into the non-linear region of operation of the VCE. Current increases because more and more charge carriers from the emitter side passing through the base side is collected by the collector, and a time comes when you will approximately get a straight line here for a fixed value of IB. Currently meaning that it starts to behave like an ideal current source, and therefore the collector current is almost independent of the value of voltage across the collector to emitter voltage, and it has got a fixed value with respect to the output current. So, what we do is now if we go on increasing the current IB current by changing the value of VBE, of course the collector current will also change, and the collector current will change by how much. So, this will be in microamperes, right, IB, whereas this will be in milliamperes. The collector current will be in milliamperes, because you multiply IB with approximate IB with a factor known as approximately equals to 100 or 100 you multiply. Why do you multiply? Because the simple reason that your emitter current is equals to a collector current, right. Your base current is just very small because of recombination. So, whatever is left is basically your collector current, and therefore the collector current IC is of the order of few milliamps here, where a base current is of the order of few microamps. Now, if you look very carefully, the region which you see in front of you, I will just show it to you by discussion here. This region from 0 to approximately this region VCE sat, this is also referred to as line. This is known as, this point where the transistor actually saturates is known as VCE sat. Is typically 0.1 to 0.2 volts is the maximum value of voltage at which the saturation tendency comes into picture, and this region is actually known as the saturation region. This region from starting from here to here, and beyond that is defined as my active region, right. Beyond that is defined as my active region. Beyond the VCE sat part, this is my active region for the NPN transistors forward active mode. So, this is the active mode. So, is basically the region. Now you see in a common emitter configuration, let us suppose, right, in a common emitter configuration, this is my emitter. Now for a fixed base current I get a fixed, for example, so we have understood two things, therefore I have a common emitter configuration, I have a saturation region, I have an active region, right. Saturation region is the region where the current, output current will be a linear or a non-linear variation on depending on the value of VCE. VCE sat is the saturated collected to emitter voltage beyond which the current will be independent of VCE, behaving like constant current source. Approximately 0.1 to 0.2 volts will be the approximate value of current technology. Also if you look very carefully that you have this IB value of the order of few microamperes, whereas this collector current is of the order of few milliamperes, right, and that you need to find out, or you need to know this basic fundamental principle. Now let us look at one small point before we move forward, that in fact inherently even without doing any drastic mathematical formulation, I can show to you that we are actually indeed doing a small amount of amplification here, and how the amplification is done I can just show it to you roughly by this diagram only. You see you generally apply the signal to the base side, right. Now for achieving amplification in a common emitter configuration, for the better any configuration, the device should be initially biased in the active region of the operation of the device. If it is not, your amplification will be a nonlinear amplification, right. In the emitters, in the active region only, you will automatically get a very linear AV. So AV or the voltage gain will not be a function of the input voltage or output voltage, it will be fixed if you bias your device in the active region. Therefore what generally people do is they apply first of all a DC bias, a DC VBE and a DC VCE, such that the device is biased in this Q point, this Q. So this is the value of VCE and this is the value of IC. So I know the value of IC as 1 milliamp and VCE as say 2 volts, right. I just take up a circuit, this value of VCE and this value of 1 milliamp we get, and then we bias it by an external DC source. Now this DC source will not change across the experiment, it will still remain the same. It will just help you to bias the device in a region or place the device in a region where amplification is possible, and not only possible but it will give you a linear amplification independent of the input voltage. Once you have fixed the DC bias, now superimposed on that you will have to give your AC bias, right. So you, what you do is you first insert a DC bias VDC and then add to it A sin omega t. This is your input signal, fine. So what will happen, I will tell you what will happen. So I have a VDC, because of VDC which is basically VBE, right, I will have a fixed value of IB. So let us suppose this is the value of IB which I am getting, this is the value of IB which I am inserting, and I am fixing the value of here. Corresponding to this my VCE value is already fixed at say 1 volt or 2 volt. Now what I do? Now I give a signal which is the input signal which is A sin omega t, let us suppose. As a result my current IB, right, will also change sinusoidally, it will change sinusoidally, right. So I have a DC bias and there will be an AC bias overriding over it, which is basically my sinusoidal signal, input signal. So I will have a sinusoidal input signal, which means that the current will once it will go from nominal value to high value, then come down, go to the bare minimum low value, then again it goes up and again it comes down, goes up, comes down, so on and so forth, which means that IB. So if your nominal value was say 0.1 and your peak to peak variation is say 0.4, then say 0.1 it goes to 0.2, 0.2, it again goes to 0.1 and again comes to minus 0.2 let us suppose, and then goes up. Let us suppose this is how it variation is. So the peak to peak variation is plus 0.4 and so on and so forth, which means that this Q point, by virtue of the signal being inserted into the base to emitter junction of the NPN common emitter configuration, this Q point will shift by 0.2 volts at the top and then go minus 0.2 volt 2 volt at the bottom in current, sorry, right. So, the base current will go, so the Q point will go top and then it will again go at the bottom, again it will go at the top, again it will go at the bottom by application of a principle. But please understand, this will give rise to a change in the current which is so much delta IC, and this is in milliamperes because we just now learned it, which means that a microampere change in the current results in a milliampere change in the output current. So, the input current changes by, let us say, 10 microamp and the output current changes by, say, 100 milliamp, right. So, del IB is this much and del IC is this much. So, if I want to find out the current gain, I will get 100 into 10 to the power minus 3, right, divided by 10 into 10 to the power minus 6. So, this cancels out, 10 into 10 to the power plus 3, right. So, automatically I get a current gain AI, current gain to be equals to approximate 10 to the power 4 times increase in current, which means that for a small change of approximately 10 microampere peak to peak change, if I get a 100 milliampere peak to peak change, I get 10 to the power 4 times AI. This, if you multiply with an external resistance R, is basically my voltage gain or a voltage change which you see, fine. So, this is what you get as a common emitter mode configuration, basic amplification which you see as far as this basic understanding is concerned, right. So, this is the common emitter configuration as far as the previous discussion which we had as far as concerned. This is the active common emitter mode configuration, active source, active forward active mode configuration with the schematic shown in this figure, right. So, as I was discussing with you, therefore, the emitter is common connection between the ground, right. Now, I think this is clear to you that the power supply must be large to keep the base collector junction reverse bias, right. Is it okay? Now, the base current is established by VBB and RB. Why? If you look at VBB, this is my VBB and this is my RB, right. So, I get IB to be equals to VBB, right. If you go from this side to this side, VBB minus VBE, right, base to emitter junction divided by RB. This is 0.7, this has to be of the order of few kilo ohms, for this to be in the order of few micron. So, this has to be order of few large value of voltage has to be, RB has to be typically very large, otherwise base will short out, right. So, what we get from here is that yes, if VBB is equals to 0, the base emitters junction will have 0 applied bias, right. Why it will have 0 applied bias? Because with VBB equals to 0, effectively your base emitter current, if I am assuming it to be ideal one, is 0. So, 0 minus 0 is 0 and I get no current available to us, and therefore, your base current and the collector current will all be 0, and this implies an cutoff condition. So, which means that if your VBE or VBB is 0, you are not able to switch on the transistor and therefore, you reach to cutoff condition. In that case, we write out VCC. VCC is what? Maybe I use the previous slide. VCC is this one, VCC, right, is equal to VCE plus ICRC. We have discussed this point, VCE. So, if you go by this loop, VCC is this is equals to ICRC, right, plus VCE. ICRC is the voltage drop here plus VCE, and that is what is given by this value. And we know that IC equals to beta times IB, right. Beta is of the order of few hundreds, only, and therefore, I get IC equals to beta times IB, right. And therefore, if IB is of the order of few microamperes, I would expect to see IC of the order of few milliamperes in this case, right. And as they was discussing, the collector current is therefore is a fraction alpha of the emitter current, and alpha is very close to 1. So, if emitter current is say 1 milliamp, you will expect to see collector current very close to 1 milliamp, because alpha is very close to 1, right. And the base current is 1 by beta of the collector current. This we have already seen just now in this case, and these are the few important parameters found in the book also, out of which these two are quite important parameters. I will not do a formal derivation here, I will leave an exercise to you, that alpha is equals to beta upon beta plus 1 and beta equals to alpha upon 1 minus alpha, right. And for therefore for alpha equals to 1 I get beta equals to infinity, right, and beta equals to infinity, and so infinity will be infinitely high value of beta you will get, right, and this is what a typical configuration. So let me therefore at this stage let me finish off with common emitter configuration understanding. When we meet next time we will start with common base and common collector, and that will take care of the effective values here. So what we have learned in this lecture is common emitter configuration module and how we can calculate the value of current and basic amplification in a common emitter configuration, and we have also learned how I can act as a switch also, right. So when beta is much larger than 1, then I get approximately alpha equals to 1 and I get IC equals to IE, which you can see from here. I get IC equals to IE, right, and therefore the collector current is approximately equals to the emitter current. Now the very important formulas which is shown in front of in this slide is one is alpha is how related to beta, and how beta and alpha related to each other is like this. In standard books which you will find, you will get the methodology for how you got this alpha and beta from basic Kirchhoff's law. We have also understood that IC is equals to alpha times IE, and therefore IC by IE is basically equals to alpha, which we have already seen. We have seen beta to be equals to IC by IB for all practical purposes. So this is what we get, or what we get from it. I just wanted to make one small important observation before we move forward, that when we referred as capital I, there is a difference between capital I and small I, right. Now capital I primarily refers to as a DC current. So whenever you have DC currents or DC biases, we refer to this as capital I, and small I is generally referred to the case when you have got AC currents. Similarly, if you have got subscripts as capital and subscript is small, then when subscript is capital you are getting a DC bias, and small means you are doing a transient analysis, right. So you should be very careful when you use these. So if I have got I and capital C, which is this case, it primarily means that I am using an AC analysis, small signal AC analysis, but I am trying to find out the total current flowing through the circuitry, right. So I have got, therefore this notation is quite important in terms of understanding this basic principle. What we also have learned in the previous slides or previous discussion is two important points, that if you look at this graph once again, if you see, then at least for the higher values of IB, your base width modulation is very large, right. So your base width modulation is quite large for large values of IB. So when IB is low, you generally do not see, or when your VB is low, you do not see large amount of base width modulation, but you see a large amount of base width modulation when you have a larger value of IB effectively with you. The second thing which you can see is that in the saturation region, right, the resistance offered is typically relatively low, whereas in the active region the resistance offered is relatively very high, right. Resistance offered by the device is very high, right, and that has to do of course with the understanding that during the saturation region, which is just before the VCE sat, we end up having the device is just going to the on state. Please understand, various books and various sources give you different regions. Some of the books also give you this region to be as the saturation region and this region to be as the active region, but we will follow the same trend for all our subsequent lectures, and we will assume that the active region is the region where you should bias the device in order to use it as an amplifier, right, and this is the active biasing which you should do in this case, right. We come to the next important configuration, and that is known as common base configuration. And in common base configuration, I will just show you, maybe I can just show you here. Okay, I do not have it in that sense, but I can show you here in a common base configuration how it works out. So common base means the base is common between emitter and collector. So if I have an NPN, and this I have been doing it for quite often now, that this emitter base will therefore be forward biased, right, and therefore this will be also, this will be reversed biased in a sense, and therefore this will be like this, right. So this is the common base CB configuration, common base configuration, right, common base configuration which you see. And as you can see, we have already discussed this time and again. This is VBB, let us suppose, and this is VCC, and you can vary both of them and so on and so forth, and you can get large amount of characteristics out of it from this characteristics. So common base configuration, as the name suggests, when we plot, therefore for a NPN VCB collector to base versus IC, right, versus IC. Now you see, quite interestingly, even when I think all of you can understand this graph, this is for a fixed emitter current. So for varying emitter current, right, IE1 greater than IE1, IE2, IE3, IE4, IE5, such that IE5 is greater than IE4 and so on and so forth, and the last one is IE1. With this condition or with this idea, what we see is that as VCB is positive, right, is positive. It primarily means, why it is positive means what? It positive means, I will just show you, it positive means this is positive. So I have biased it positive. So when it is zero biased, even when it is zero biased, you will see that you still have large amount of current flowing through the device, and the reason being very simple, that even at zero bias you have applied such a large electric field because of VBB, that electrons which were predominantly my emitter current IE, right, pass through the base region very fast, and they cross through this region very fast and reach the collector side. Though we didn't apply any potential, positive potential on the collector side, on the IC side, collector side, but still a current from the emitter side is reaching towards the collector side in a very fast paced manner. And the reason is that though a bias was not applied, but the velocity is so strong that it can easily cross the base region and reach the collector side. And therefore, if you see very carefully, that you will always have a current which is equals to alpha into IE, because remember alpha was defined as IC by IE, right. So IC will be nothing but alpha times IE. So I get alpha times IE, right. Similarly IE1, IE2, IE3, IE4, IE5. Now if you increase VCB, it is almost constant independent, that we have already discussed why is it like that. But then it means that you have to make your VCB go in forward bias in order to stop the current flow, and I think you can understand why. So you have to give a negative potential here, right, in order to repel the electrons to move in this direction and not reach here. Is this concept clear? Which means that that you minimum have to give this to be approximately equals to 0.4 to 0.5 with a negative sign, so that it is in the cutoff mode. So therefore this is known as a forward active mode, as I have written here. This is the forward active mode, and this is the cutoff mode which you see. This is the cutoff mode, right. We define this to be as the saturation mode, and this to be as the cutoff. So you can do a cutoff here. So this much amount of minimum amount of VCB has to be provided in order for the device to be in cutoff. So if you want to switch on the device, you have to bias your device to go from VCB of minus 0.5 volts to approximately 0 volts for all practical purposes, right. And this though it has been shown in a much greater sense, but the drop is very drastic. It is a very fast drop which you see here, right, and it is almost a straight line curve for a common base configuration. But what you will see here, alpha is very close to 1, so you do not get any amplification out of common base configuration, because the amount of emitter current you are getting is approximately the same as the collector base configuration, right, and that is the basic idea of a common base collector, common base configuration. We do have a common collector configuration which is there with us, in which the collector is common, so or collector grounded configuration, in which the collector is grounded or is common between the base and emitter. RB is the base resistance and RE is the emitter resistance, and we apply a minus VEE here in order to bias the device into the active region of operation. Now if you look very carefully here, IB, the base current will be equals to VEE, VEE is this much, minus VBE, which is the voltage drop across this much, divided by RB, which is the resistance here, plus beta plus 1, which is beta plus 1 is the effective value of alpha, which you see. IC equals to beta times IB, IE equals to therefore beta plus 1 IB, and VC equals to VE minus IERE. So this will give you, but common collector is not very seldom used. It is generally used for impedance matching, but generally not used for any other purposes. Most commonly used is common emitter configuration device, and that is the most commonly used configuration here. We end today's topic by doing two things, by seeing the circuit symbols. We have already seen this, that arrow pointed outwards, which is this one, primarily means it is the direction of the holes. So holes move from base to emitter, which primarily means that the electrons are moving inwards, and therefore this is basically an NPN transistor, right. And since it is a PNP transistor, since holes are moving from emitter towards the base side, the region is shown in this manner, right. So you have to convention, in the sign convention, you just have to worry about the direction of the arrow, right. The arrowhead direction gives you the direction of the holes, right, and that is what is shown in this diagram. Let me recapitulate for both the transistors, and that will take care of approximately all the understanding of common emitter, common base, common collector. IC, for if you look at the collector current is given by this, and for one you can see, other we can always learn. IE equals to IC by alpha, I get this. IB equals to IC by beta, I get this. For both the transistors, I will get automatically IE equals to IC plus IB, because Kirchhoff's current law cannot be violated. IC equals to beta times IB, right. IE equals to actually equals to 1 plus beta, but beta is, since it is very large as compared to 1, I can approximate this as IE equals to beta times IB, right. Alpha equals to beta upon beta plus 1, and beta equals to alpha upon 1 minus alpha, and this is how you show the values of it. So with this let me thank you and give you an idea about what we did in the previous lecture series, that we have understood therefore the various configurations of working of a PNP and NPN transistor, and which one is the best. So the best option available to us is the common emitter for voltage amplification purposes. We can use common emitter as a switch as well. We can also use common base as a switch for our practical purposes. When we meet next time, we will do certain other applications of BJT, and we will do Ebers-Moll model for the BJT. Thank you very much.